and welcome to Algebra 2 with Mr. Clausen. Today, we're going to talk about solving polynomials using the sum or difference of cubes and U-Substitution. So we're going to get started by talking about factoring polynomials using the sum and difference of cubes, and then to move on to the second skill of the lesson, we're going to talk about factoring and solving polynomials using quadratic patterns or U-Substitution. So let's get started. So when we talk about factoring polynomials using the sum and difference of cubes, this is the formula. So if your teacher allows you to use a note card or notes on your exam, it's good to write this down. And if you've never seen this plus or minus notation here like this, you'll see that some of them are like plus on top of minus and minus on top of plus. And if you ever see this, all it's saying is that we're combining two equations in one. So one of them is that you have a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. So again, this is the first one where the plus sign on top, and the minus sign on top are applied to the first one. And the other equation that I can represent is a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. So if it's hard to look at this equation and identify the two different aspects of it, there's nothing wrong with writing them separately and using them in that way. But what we want to do is, much like factoring the difference of squares, the difference with factoring the difference of cubes is that you need to look for an a value that's cubed and a b value that's cubed in a given situation. So let's look at a simple example like x cubed plus 64. So if we're looking at this, and I am suspicious that this fits into cubes or squares, well, first I'm just going to notice the third power, okay? If it's the sixth power, the same thing will apply. And I'm just going to go and can I split this into three equal products? Well, yeah, I can get x times x times x. And the same thing I can do with 64. I can go 4 times 4 times 4. 4 times 4 is 16 times 4 is 64. So I can see that I can take a cube root of both of these and get a specific value. Okay, so if we see this situation occur and we can factor this polynomial using the difference or sum of cubes because it's a positive sign here, I'm going to take this example and I'm going to go, hey, let's take this where a is equal to x and b is equal to 4 and plug it into this equation here. So if I see this, I can now go x plus 4 times x squared minus 4x plus 16. And I just factored x cubed plus 16 and got this factored out polynomial. And one of the things that's really useful about this is if you have to find solutions for a given polynomial, we can't just take the cube root of both sides and say that x is equal to 4. That is only one of the roots, which is represented by this binomial. And if we can break down a cubic binomial into a normal binomial by a quadratic trinomial, we now have all these other techniques that we've talked about previously in this class, but we now have some tools though that we can use to find these other roots and go and factor this out accordingly. But this breaks it down to a simple quadratic equation that we could then use the quadratic formula on. So with that said, we can go and we can simply factor out some of these more complicated higher order polynomials and then look at them in a little bit different light. Another example would be a situation like 125x cubed minus 27 equals 0. So again, whenever we're using the situation, it doesn't have to equal 0 on the other side. A lot of times, I'm just going to move it over and I'm going to see what happens if it's not there. But again, we're going to look at a situation like this and I'm going to see this key indicator here and I'm going to go, well, is 125, can that be cubed? Can it be under a cube root? Well, if we say 5 times 5 times 5, or take the cube root of it with our calculator, we'll see that the cube root of 125 is 5. 5 times 5 is 25, times 5 is 125. And we can do the same thing with the x's. We can go x, x, x. And what that allows us to do is we can say that a is equal to 5x in terms of the cube. And a cubed would equal 125x cubed, okay, which fits into this parameter of our sum and difference of cubes formula. And the same applies to the 27. We can say 3 times 3 times 3 is equal to 27. So b is equal to 3. B cubed is equal to 27. And again, you don't have to factor all this out. If you have a calculator, you know, you can very easily take the cube root, or if you don't know how to do a cube root, you can always put like 125x cubed in parentheses and then take the 1/3 root. That would be the same thing. I guess you wouldn't be able to put the x cubed in, but you could at least put the 125 in and check that and see if it all works out to your advantage. So with that in mind, now that we know the b and the a value, if you identify it's a difference of cubes, what I want you to be able to do is take this equation and then split them apart. Because if we can take a higher order polynomial and crack it down into a binomial with a quadratic trinomial, you've just made your life significantly easier in terms of factoring out polynomials and breaking it apart into all of its individual roots. So let's look at this situation. A is 5x, b is 3. So we have 5x cubed minus 3 cubed, and this will equal 5x minus 3, because we're using the bottom half here, because we're using the bottom part there. That's the binomial, times 25x squared plus, because we're using the bottom half of the equation, 5x times 3, which would be 15x plus 9, okay? And this would be the difference of cubes for this given cubic function. All right. So now that I showed you a couple examples, we'll move on to quadratic patterning or U-Substitution. And this is another method that is extremely useful when it arises. So if you come up to a situation like this, we can tell that this is not a difference of cubes or a sum of cubes. There's no way to ever split that apart. But we do have a situation where there's a higher ordered polynomial. We have a 4th power polynomial here. And the first thing that I would do if I see this is like, oh, like, man, I gotta go and do synthetic division twice or something like that if I ever wanted to break this apart. But the thing is I see that x to the 4th and x squared, I see these are both factors of 2. And the same could hold true if you had like x to the 6th power and x to the 3rd power. You could look at the 6 and the 3 and say, hey, this has a factor of 3. Or let's say x to the 8th power and x to the 4th power. These, if you looked at them and they were present in a given situation, this has a factor of 4. And what this allows us to do is it allows us to go take a higher ordered polynomial and to use a technique called U-Substitution. And I'll show you how this works. So what we do is with U-Substitution is we substitute u as a variable and we substitute it based on the factor that is present. So for an example, we set u and we say we set it equal to x squared. Now why might we do this? Well, we do this because if we see quadratic patterning, what this allows us to do is it allows us to take this really gross quadratic trinomial and allows us to rewrite it as u squared plus 8u minus 20. So now we just took this really gross quadratic trinomial and we turned it into a quadratic trinomial, which is much easier to process and analyze than the quadratic one. So if you get this situation, we can substitute this in, and then we can start thinking about our previous chapter techniques and saying like, well, Okay, if we have 8 here and we have 20 here, let's look at our factors. And oh, if we go negative 2 and 10, and we add those together, that gives us 8. So these are our factors, and this is the center term. So what this allows us to do, still using the u terms, is we can say u minus 2 times u plus 10 is the factored version of this quadratic trinomial, but we're doing it in terms of u. So if we do this, what we can find is that after we factor this out, after we perform the factoring of the quadratic patterned situation, what we're going to do is re-substitute in the x squared for u. And this gets you somewhere, and I'll show you why. The reason why is if we can plug in x squared for u, we now have x squared minus 2, and we have x squared plus 10. And if this is all equal to 0 and you want to find the zeros of a given polynomial, we can now use the zero product property. And we now can split this apart and say, all right, x squared minus 2 equals 0. And we can say that x squared equals 2 if we add 2 to both sides. And we can take the square root of both sides, and as a result say that x has solutions of plus or minus the square root of 2. And something where you wouldn't be even close to finding by yourself, and even if you graphed, you would really be limited because you wouldn't be able to find the exact solutions. You would find some weird decimal, and you wouldn't be able to find that, which isn't really good enough if you need an exact number. So the other situation here, okay, we can say x squared plus 10 equals 0, and we can subtract 10 from both sides. And now what we can say is x squared equals negative 10, and what you'll find is we'll square both sides. Oh, and guess what? Even if you did graph this, you'd only see 2 of the solutions. So in this given instance, we would have x is equal to plus or minus I times the square root of 10. And those would be 2 of your given solutions. Okay, so it can be a very useful technique because, like in the previous video, I was talking about like these factoring techniques and finding multiplicities. And as long as you have real or irrational multiplicity, so to speak, you know, you can find things relatively quickly. But if you have non-real numbers, you actually can't see those. So with that in mind, it gives you a quick way to find some solutions really quickly. Another example, let's look at a to the 4th minus 5a squared plus 4. So in this given situation, what we're going to do is, I see the quadratic pattern here again, and what I'm going to say is that a squared is equal to u. So again, we're taking this quadratic trinomial and we're turning it into a quadratic using U-substitution. That's the whole point of quadratic patterning. And then we're going to say minus 1, minus 4. If we add those two numbers together, we'll get minus 5. We just found our factors. Okay, stuff that you probably feel pretty good about right now if you've been following these videos. So u minus 1 and u minus 4. And let's just set this all equal to 0 because we're going to take advantage of the zero product property to solve this polynomial and find the zeros. So again, let's take the u, let's resubstitute it back in. We'll get a squared minus 1 times a squared minus 4. And now we start splitting it apart. Now, before we start just going and plugging everything in, I'm going to point out here is that both of these are difference of squares. And difference of squares, remember, is a squared minus b squared is equal to a plus b and a minus b in terms of the formula. So when you see these, take advantage of them. So now we have a minus 1 times a plus 1. And a squared minus 4 would be a minus 2 times a plus 2, all equals 0. And in this situation, we can see that our zeros, or roots, is simply 1, -1, 2, -2. And now we have all of our roots identified. So it's a really quick way to find some solutions from really gross polynomials down to simpler ones. And we're just trying to build up our toolbox and find all of these different variations. With that said, I hope that you found this video helpful and that it broadened your understanding of tools that we can use to dissect higher order polynomials. And hope you have a great rest of your day, and let's do math.